Have you ever wondered how Agentic AI actually thinks? It sounds like pure magic, but it's not. In fact, it's exactly like having a professional chef living in your house. Imagine you want to eat crispy fried potatoes, but you don't know the first thing about cooking. What do? You head to the market, buy some fresh, raw potatoes, come back home, and hand them over to your chef. You give a simple order. Chef, fry these potatoes. After some time, the chef walks out and serves you a perfect plate of golden fries. But have you ever wondered how the chef actually prepared those fries for you? It comes down to 3 main steps. Step 1, peeling the potatoes. Step 2, slicing them into pieces. Step 3, frying them in hot oil. To do this, the chef needs physical tools, a peeler for peeling, a slicer for slicing, and a fryer for frying. But tools are useless unless you know how and when to use them. The chef relies on an internal instruction set, a recipe book, that explains exactly how to coordinate those tools to turn a raw market potato into delicious French fries. Now, let's jump from the kitchen into the world of computer science to understand Agentic AI. Instead of a potato, we're going to give our AI agent a raw data text file named sparrow.txt. And instead of making fries, our goal is to get a detailed information report about how many words, vowels, and consonants are present inside that file. In this digital kitchen, our chef is a Python function called runAgent. But a chef needs a mind to think, right? The brain inside our chef's head is a local LLM named Gemma 4 2.3 billion parameters. The raw potato we brought from the market is our file, sparrow.txt. Our kitchen tools are 3 specific Python functions: count words, count vowels and consonants, and save analysis. The recipe book that tells our chef's brain how to use those tools is called the tool schema. And finally, our finished plate of crispy potato fries is the output file, information.txt. Our exact query to the agent is read the file sparrow.txt and count the number of words as well as the number of vowels and consonants. Later on, create another text file, information.txt, and write the information in a structured manner. One important note. Before we can start our digital kitchen, we need to install our head chef's brain. We'll be using Ollama, which lets us run powerful AI models right on our own computer. So let's jump into the explanation of the code. Before we dive into the logic, we need to prepare our environment. We'll run these 3 commands to get everything ready. First, Ollama poll Gemma 4 2.3 billion parameters. Think of this as hiring our head chef. This command downloads the AI model to your local machine, so it's ready to think, process, and make decisions without needing the internet. It's the installation of the brain we discussed. Next, import JSON. This is a built-in Python tool that allows our script to handle the recipe book. It helps Python read and organize the structured data we need to communicate with the AI. Finally, import Ollama. This is the communication pipe. It's the bridge that connects our Python code to the Ollama brain we just pulled. Without this, our script would be like a chef trying to talk to an empty room. With these 3 things in place, we have our chef, our communication channel, and our data handler. Now, let's jump into the code. Let's look at the code to see how the magic happens. Our chef, runAgent, runs a continuous while-true loop. This loop is the heartbeat of our kitchen. It creates a constant back-and-forth conversation between our chef's hands, the Python controller, and the chef's brain, Gemma 4 2.3 billion parameters. The decision. The chef's brain reads your query, looks at the recipe book, the schema, and realizes it cannot fry before peeling. So the brain commands the chef, I need to use the count words tool. The action. The chef, runAgent, executes that command, grabs the physical tool, counts the words in sparrow.txt, and hands the raw number back to its brain. The next step, the brain looks at the result, checks the recipe book again, and says, "Great, now use the count vowels and consonants tool." This loop keeps running, thinking, acting, and observing until the final function, save analysis, triggers the fryer and writes everything into information.txt. The brain didn't do the physical work, and the chef didn't make the creative decisions. Together, they orchestrated the tools perfectly to give you exactly what you ordered. Let's look at our very first kitchen station, the count words function. Remember, this is our peeler. Its entire job is to take a raw file and strip it down to find the total word count. Let's break it down line by line. First, we define the function and give it a parameter called file name. This is us telling the kitchen, hey, if you want to use the peeler, you have to hand it a specific potato, or in this case, a specific text file, like sparrow.txt. Next, we see this line, with open, file name, R, encoding equals UTF-8 as F. The with open statement is like safely opening the kitchen cabinet where our file is stored. The R means we are opening it in read mode because we just want to look at the ingredients, not change them. And encoding equals UTF-8 ensures our chef can read all kinds of text and characters without getting confused. Inside that cabinet, we have content equals f.read. This reads the entire text file from start to finish and stores it as a giant block of text. Then comes words equals content.split. This is where we chop up that giant block of text. The dot split function automatically breaks the text apart wherever there was a space. So it turns a long paragraph into a neat list of individual words. Finally, we have return len words. The len function stands for length. It simply counts how many items are in our chopped up list, and return hands that final total word count right back to our chef's brain. So when the chef's brain asks for the word count, this station opens the file, chops the text into individual words, counts them, and reports back with the exact number. Now, let's move on to our second kitchen station, the count vowels and consonants function. Think of this as our slicer. Its job is to take that same raw text file, sort through it character by character, and separate them into two different bowls, one for vowels and one for consonants. Let's see how it works line by line. At the very top, we define our reference string. Vowels equals A-E-I-O-U, capital A-E-I-O-U. This is like putting a picture of our target ingredients on the wall, so the slicer knows exactly what a vowel looks like, whether it's lowercase or uppercase. Next, we set up our two empty bowls, V count equals 0 and C count equals 0. Right now, our counters are at 0, waiting for the ingredients to roll in. Just like before, we use with open, file name, R, encoding equals UTF-8 as to safely unlock our file cabinet in read-only mode, and we load the entire text into memory using content equals f.read. Now here comes the clever sorting machine, a for loop. For char in content means our slicer is going to look at every single individual letter, space, and punctuation mark in the file, one by one. Now we arrive at our third and final kitchen station, the save analysis function. If the first two functions were our peeler and our slicer, think of this one as our packaging and plating station. This is where we take all of our processed ingredients, put them together, and serve them up beautifully for the customer. Let's see how this formatting station works line by line. At the very top, look at the inputs this function expects: file name, word count, vowel count, and consonant count. This means our function isn't searching a file anymore. It's waiting for our chef's brain to hand it the raw numbers we just calculated. Once it has those numbers, it creates result text. We use a Python multi-line F string here to style our report. It creates a clean layout with a clear header, a divider line, and injects our exact word, vowel, and consonant counts right into the text using curly braces. This is like perfectly arranging our crispy fries in a clean, professional serving box. Next, we look at output name equals file name. In our example, the user requested the output to be called information.txt, so this line assigns that exact name to our final package. Then we see a crucial command, with open output name, W, encoding equals UTF-8 as F. Notice the W right here. Unlike the earlier functions where we used R to read a file, here we use W for write mode. This tells Python to open up a brand new empty text file named information.txt on your hard drive, completely ready to be filled. Inside that file, we run f.write result text. This physically pours our beautifully formatted report straight into the text document and saves it. Finally, the station finishes its job with return F, report saved to output name. It sends a completion token back to the head chef saying, order complete. The dish is boxed up, labeled as information.txt, and waiting on the counter. And that is how our 3 tool functions work.
Now that we've built our 3 individual kitchen stations, we need a way to organize them so our chef can actually reach them. That brings us to this small but incredibly important piece of code, the tools dictionary. Think of this dictionary as our physical tool rack on the kitchen wall. On the left side, inside the quotation marks, we have the labels on the rack. Count words, count vowels and consonants, and save analysis. These are just plain text strings. They represent the names the AI chef's brain will shout out when it wants to get something done. On the right side, without quotation marks, we have the actual tools themselves. Count words, count vowels and consonants, and save analysis. These point directly to the actual Python functions we just finished writing. Why do we do this? Well, when our AI brain, Gemma 4.2.3 billion parameters, is thinking inside the loop, it can't directly execute Python code. It can only talk to us in text. So when it decides it's time to peel a potato, it looks at its manual and shouts the text string, count words. Our Python script catches that text, looks up the count words label on this tool rack, grabs the real working count words function next to it, and runs it. This dictionary is the ultimate bridge that lets a text command from an AI model trigger real physical execution on your computer.
Now, remember earlier when I mentioned that our chef's brain, Gemma 4.2.3 billion parameters, doesn't inherently know what tools exist in our kitchen? That brings us to this JSON block called the tools_schema. Think of this as the recipe book or the user manual for our AI. We pass this exact structure directly to our model so it understands its boundaries and capabilities. Let's look at the structure of just the first tool to see how it's written. Every tool in this list starts with type equals function. This tells the AI, hey, this isn't just background information. This is a real executable action that you can call upon. Inside the function block, we give it a name, which matches our tool label, count words. Next is the most important part for an LLM, the description. It says, read a text file and return the total word count. The AI reads this plain English description to figure out when to use this tool. When you ask it to count words, it reads this manual, matches your intent, and thinks, I need to use the count words function. But the AI also needs to know how to use the tool. That's what the parameters block is for. It tells the AI, if you want to use this tool, you must supply an object called file name, which must be a string representing the path to the text file to be read. Finally, notice this line, required: file name. This is a strict rule in the manual. It tells the AI, do not try to call this tool unless you have a file name to pass to it. Running it empty will break the kitchen. As we scroll down, you'll see the exact same layout for count vowels and consonants, which acts as our slicer. But take a close look at our final tool at the bottom, save analysis. Look at how detailed its parameters are. We aren't just telling it the names of the inputs, we've added custom descriptions for each one. We explicitly tell the AI that file name is the name of the new output file to be created, like information.txt, while word count, vowel count, and consonant count are the integer metrics it calculated from the previous steps. And all 4 are marked as required. This tells the chef's brain,
You cannot run the plating station to package the final report until you have successfully gathered all 3 pieces of data from the peeler and the slicer stations, and you know what to name the final dish. By handing this highly descriptive schema to our model, we give it the exact blueprint it needs to make autonomous, smart decisions inside our code.
Now we have finally arrived at the brain surgery of our script, the run agent function. Remember, this function is our head chef. It doesn't peel, slice, or fry on its own. Its job is to stand in the center of the kitchen, run the execution loop, and manage the workflow. Let's track how this code executes your order from start to finish. At the very top, we define def run agent user query. The user query is the exact order you shouted into the kitchen, our request to read sparrow.txt, count the components, and save the report. Right below that, we create an empty order tracking sheet. Messages equals user content user query. This list is the active memory of our kitchen. Every single order, decision, and ingredient count will be recorded here, so nobody loses track of what's happening. Then we enter the infinite loop, while true. This is the heartbeat of Agentic AI. It is the continuous cycle of thinking, acting, observing. Inside the loop, the first thing the chef does is ask the brain what to do. We call Ollama.chat and hand over 3 things: the model, Gemma 4, 2.3 billion parameters, our entire messages memory log, and our tool schema recipe book. The brain looks at the manual, looks at our query, and passes back a response. Now, our chef has to handle 2 possible scenarios. Scenario 1, the brain just wants to talk. Look at this if statement. If not, response.message.tool calls. If the brain doesn't ask for any tools, it means the job is done. The chef prints the final message to the console with printf agent response.message.content, hits break, and safely exits the kitchen. Scenario 2, the brain requests a tool. If the brain does ask for a tool, the code jumps down to this for loop. For tool in response.message.tool calls. The chef extracts 2 vital pieces of text: the function name the brain wants to call,
And the args, the specific ingredients or file names the brain chose to pass. Then the magic bridge happens on this exact line. Result equals tools, function name, args. Remember our tool rack dictionary from earlier? The chef takes the text function name requested by the brain, looks it up on the rack, pulls down the real physical Python function, like count words, and executes it instantly on your machine using the brain's arguments. Once the tool finishes running, we get a result. But here is the most critical step in all of Agentic AI. Messages.append, response.message. Messages.append, role, tool. Content, string, result. The chef takes the brain's decision and the physical tool's output, like, hey brain, I ran the peeler and found 150 words, and pins them both directly back onto our messages tracking sheet. Because we are in a while true loop, the script immediately loops back to the top. It calls Ollama.chat again, but this time the brain sees the new tool results in the memory log. It updates its thinking and says, excellent, the peeling is done. Now let's call the slicer. This cycle repeats seamlessly until the final report is safely fried and saved.
And now we have finally reached the ultimate trigger line, the actual execution of our code. This is the moment where we sit down at the restaurant table and place our official order. We call our head chef function, run agent, and inside the parentheses, we pass our exact plain English instruction as the user query. Let's read what we are asking our agent to do. Read the file sparrow.txt and count the number of words as well as the number of vowels and consonants. Later on, create another text file, information.txt, and write the information in a structured manner. Notice how we aren't writing code to tell it how to execute these steps line by line. We aren't saying first run function A, save the variable, then pass it to function B. Instead,
we are handing a raw conversational sentence to our agent. When this line executes, it kicks off that entire while true heartbeat loop we just went over. Our chef's brain, Gemma 4, 2.3 billion parameters, will look at this text, check the recipe book, and say, aha, to fulfill this order, I need to look at sparrow.txt and call count words first. It executes the peeler, records the word count, loops back, and realizes, okay, now I need to call count vowels and consonants to get the rest of the ingredients. Finally, it looks at all the data it gathered, matches the last part of your prompt about creating a structured text file, and triggers our packaging station, Save Analysis. When the terminal stops running, you will suddenly see a brand new file appear in your directory named information.txt, containing your beautifully structured report. And that is how you build a fully autonomous, tool-using AI agent right on your own computer using Ollama and Python.
And that's how you bring intelligence into your own code. If you enjoyed this journey from the kitchen to the digital agent, and if you found this explanation helpful for your own projects, please share this video with a friend. And don't forget to subscribe to the channel, Contributor Snill, for more deep dives into the world of AI and systems engineering. Thanks for watching, and I'll see you in the next one.